Hello everyone, welcome to our pre-calculus pre-recording video. This is about irrational and complex zeros of polynomials. So in our last lesson we try to find out the real zeros of polynomial functions, and sometimes we have found like irreducible terms, but we will extend our concepts so that we can actually reduce it where we get some irreducible terms. This lesson is somewhat theory heavy, so keep that in mind. We have irrational zeros of polynomials, irreducible quadratic factors, imaginary and complex numbers, fundamental theorem of algebra, complex zeros of polynomials. These are the agenda for our today's lesson. Let's begin. So intermediate value theorem tells us that for a certain value, let's say a, if the function is negative, and for another value b, if the function is positive, then there must be one real zero in between them. So 0 is here. There must be a 0 in between them. The reason is why it is true. The reason is we cannot go from this point to this point without crossing this x-axis. Without crossing that x-axis, we cannot go there. There is no way to go there without crossing this x-axis. And the crossing of this x-axis is actually the zeros of the function. I mean, if you cross here, if you cross here, they gives us the zeros. And so far we discussed our real zeros. So all the cross, like here you cross, here you cross, here you cross, all of them are the real zeros of your function. So here what it tells, let me repeat it once again. This is intermediate value theorem. For one value, if you get some negative answer in the function, and for another value, if you get a positive answer in the function, for in between that two value, in this case a and b, there must be a real zero. This is what intermediate value theorem tells us. Let me give you an example. Some of you may get like think what actually it means. Let me tell you that. Let's say for any function, if you get f of 1 equals to, let's just saying, for example, suppose you get 2.31, something like this. Then f of 2 equals to, let's say you get minus 0. Let's say it's minus 0.3. That means in between 1 and 2, there must be a shift of your graph. From positive 2.31, the graph came to negative value. That means the graph crossed your x-axis somewhere. This is what it means. So intermediate value theorem tells you that between 1 and 2, there must be a real zero because there is a change in sign. Okay, so this is what this theorem tells. And then not every real zero of the polynomial is irrational, so they can have different things. That's what is the scope of this lesson. This is again the proof that what I said, like if you have minus 2 and minus 1, in between this, if you have something, f of minus 2 comes minus 5, f of 0 comes 1, f of 2 comes 7. So basically there must be one real zero in between them. Okay, since there is a change in sign. That is the reason. Now, how can we approximate it? How do we know actually exactly where we have the real zero? For that, we can put many values and check where it can be. Like f of minus 1.1 minus. Suppose if we know that in between 1 and 2 we have real zeros, minus 1 and minus 2 we have real zeros, let's say in this case. So we put all these small values in between 1 and 2, like minus 1.1, minus 1.2, minus 1.3. then we will be able to approximate where actually it happens. Now that's not the end. Still you will not get the answer there, because let's say in this case actually you will get minus, in between minus 1.3 and minus 1.4 you get a positive and negative. So that means in between minus 1.3 and minus 1.4 you have your real zero, but that's not the answer. So you will have to split this part once again. And this is not what we do nowadays. Computer does all these things if necessary to find it out. But this is the way. This is a way to find out the roots, to find out the solution. Okay. Usually this is done by computer, not the human being. But this is the theory how it is done. Now you will try to find out the value of the function if this and this, and if how many zeros we will get in between. Okay, located between. You can just put the value and then think about it. How many zeros you will get, and of course see the change of sign. This is positive -1. This is negative -1. This is positive +1. That means there must be a real zero in between these two values, because graph cross the x-axis somewhere between -1 and 0. Okay, then again from 0 to 1, if x value is 0 and if x value is 1, again there is a change in sign, so there must be something there. This is the idea for finding the zeros. If you see the change in sign here, see, this is +1, this is -1. So there must be a real zero in between them, in between these two. This is the idea. And this is the idea. And actually, if you can tell that, that is also a success. Like you do not know exactly what is the answer, but you know that between 1 and 2 or between -1 and 0, you have a real zero. Because later we can approximate more and more and more to find out actual answer if necessary. But as we said, this is not a human being's task anymore. This is done by computer. But of course, the human being has to tell the computer how to find it. All right. So this is another slides that we discussed in our previous lesson. And this is like irreducible quadratic factors. You have seen that if we try to factor it, so if we start factoring, we can factor it x plus 1, x minus 3, and then there is something which we cannot reduce because that's not intersect the x-axis. So we have decided that is irreducible factor. Okay. All right. Now, if we introduce a new kind of number, then actually we can work with that, and that is one of the important part of this lesson. Imaginary unit. There is no real number x such that x is square equal to -1, because then it becomes root of -1. So if we define I square equal to -1, then actually we can define this kind of thing. I square equal to -1. That means now we have a root of -1 equal to I. So now see this kind of root of -9, we can separate it, root of -1 and root of 9. Then root of -1 equal to I, so we can write 3i here. That means square root of -9 equals to 3i. Now we can write. But previously we used to say this is not defined. Okay, this is defined only if we introduce the imaginary unit. That is what is called imaginary unit. Power of I. So if we try to work with the power of I, how it works, I to the power I means 1 I, because that's just like the same thing. Power 1 does not just, it do not change anything. Then I square equal to -1, that's the definition. I square equal to -1. I cube equal to -I. How it happens is given here. I cube means I square into I. So I square means -1 into I, so we get -I. I to the power 4 equals to 1, because I square into I square, that means -1 into -1. -1 into -1 means 1. I to the power 5, so I to the power 5 means I square into I. I square minus minus plus, then you have I only. So the power of I actually gives us like different outputs. We will have to be careful about how it works. All these powers, and of course all of them will work if you just break it down, then this will work. Now complex number. So far we have discussed in our last lesson. We said that real number, numbers, all the classification we try to do here, like natural number, integer number, rational, irrational, real. All the numbers are real number, of course, here. And then in between irrational number, we said that some are algebraic and some are transcendental. All these things we discussed. Now, what about this I related? Let's say a plus bi, or just only bi, or I related. Since we introduced now this imaginary part, so where they will go in our this chart? In this chart, actually, they will form the complex number. This is the complex number. Actually, technically, all the numbers also you can say complex number. If the imaginary part becomes 0, then actually these numbers also can become the complex number, and they are actually. So we have complex number. In the complex number, you will notice that there is the imaginary part and the real part. Together, they form the complex. Okay, imaginary part 3i and real part 9. Together they form complex numbers. A plus bi, a is the real part, b is the imaginary part, bi. Both of this together is the imaginary part. And of course I is defined, so already we know it. For example, some of the examples are given here. See, if this imaginary part becomes 0, then actually we get minus 5. So this is how this complex number can have all the things inside. All of them are contained within this complex part. This is how it can get, because if the imaginary part becomes 0, then actually all these numbers, this is just an integer minus 5. Minus 5 is also a complex number in that manner. So this is like a technical proof. How can a just simple number can be a complex number? So complex number can be added, multiplied, divided, etc., etc. But we will have to be careful about working with the like terms, because let's say 3 and 8, so they are the like terms because they are real part, and then 5i minus 2i, they are the like terms. So we cannot mix them together, but we can work with their real part and the complex part. Then we can add, subtract, etc., etc. But we will have to be careful about the like terms. Like that. Suppose here 8 minus 2i, we cannot say that okay, 8 minus 2 equal to 6, then I. Not like that, because they are different part. So yeah. What is the value of 4? What is the value of 4 minus? The answer is written here, 4 plus 3i, then minus. So you give a subtraction due to the minus sign, there is minus 1, then minus minus plus, it becomes positive 7i. So positive 7i and then 3i, total is 10i. Minus 4 and minus 1 becomes minus 5. Okay, this is subtraction, then this is multiplication. Just like the simple multiplication or the FOIL method, if you use, then minus 4 and multiply this, then minus 3i, then multiply this, and then add, subtract, whatever comes there, you will get your solution. So this is how we do this addition, subtraction, or multiplication, this kind of operation in the complex number. Now, one important thing, conjugate of complex numbers. 3 plus 2i and 3 minus 2i, these two, this is only positive and negative, this sign gap. This pair, this kind of pair is called complex conjugate, where you have everything same, just only in between them their sign is different. This kind of pair is called complex conjugate. They will come a lot of time in our discussion. Complex conjugate. Same thing, just the sign is different. Complex conjugate, if you multiply them, they gives us a real number. Okay, they gives us a real number. The complex conjugate, this is the a plus bi and a minus bi. This kind of pair is called complex conjugate. And as you can see, we will get the imaginary part gets cancelled out if you multiply them. So we have just only there, we just have only their real part. Actually, if you look at this, a square plus b square, how it is matching with this? See, this is actually easy. Once you know this thing, then actually you can use it from here. If you have 3 plus 2i, 3 minus 2i, so the answer will be actually 3 square plus 2 square, and 3 square plus 2 square equal to 13, because 3 square means 9, 2 square means 4. So from these numbers, without doing all these things, you can actually just work with 3 and 2 if you can understand that they are complex conjugate. Okay, so for the complex conjugate, we can use this relation to find out what will be our, if we multiply, what will be the solution. We'll talk about why this complex conjugate is important. We'll talk about that. So these are the, you will have to find out here what are their conjugate. Minus 6 plus I, 8 minus 5i, just only 4i, then what is their conjugate? Think about it. If you cannot find out, we can discuss in the class. But I hope from this you have the idea what to do with this. Now complex zeros are factors. So this one, that irreducible kind of thing. So when you use the quadratic formula, we actually get minus 1 plus minus root of minus 7 divided by 2. Previously, we used to say that, okay, from here we cannot find any answer since this is root of minus 7. Now, since we defined root of minus 1 equal to I, now we can actually write root 7 divided by 2. So we get two answers. One is minus half plus root 7 divided by 2i, or minus half minus this. See one important distinction between these two numbers. Both of the numbers, all the things are same actually, just only positive sign here, just only here the positive sign and the negative sign are different. This positive sign and this negative sign is different. Everything else is same. One is positive, another one is negative. So if everything is same, only sign is different in between them, then what it is called? It is called complex conjugate. Complex conjugate. This will tell you actually another theorem which is coming up. In fact, okay. In fact, always they will come in conjugate. Always they will come in conjugate. Okay. And this is a checking. Suppose in our previous all the lesson, you know that if you get a real zero, suppose x square, let's say x square minus twice x. Suppose f(x) equals to one of the zeros of this function is x equals to 2. So if you put x equals to 2 here, then the function becomes 0. 4 minus 4 equals to 0. So if this is a real zero of the function, then we can prove it in another way, that is called, we can plug this value in the function and the function will become 0. Alright, that's good. But what will happen about this? How can we prove that this is also a 0 of this function, How can we prove it? This is kind of crazy, like these numbers. In fact, actually we can do that. And the method is exactly the same. You just put, this is x equals to, so you just put, instead of x, you just put this number here. So you will get, this is x, that means this number is square, it will be, so this number is square, then my plus x, so you write plus x, then plus 2, Then you do some addition subtraction, and you will see the answer will come 0. See, 1 by 4 minus 1 by 4, this and this, this and this. If you just do it, you will see that all of them will cancel out. This is 1 by 4, this is minus 7 by 4, this is minus half. Together all of this number becomes 2, and then this is root 7i by 2, this is minus root 7i by 2, they will cancel out. This 2 is positive, and all this fraction here will make a 2, and that will cancel out each other. Answer is 0. And if you try with this number, with this another 0, then actually that will also make it 0. You can check, you can put this value here, and you can follow this calculation, similar type of pattern of calculation. You will see answer will come 0. That is what it is telling actually. That means that these are true, these are real, these are actual. I mean, the roots are real. Roots are real means roots are true. I mean, this real actually means that they are not real number, they are complex. Okay, so this is how we can prove it, and this is how we can find out the answer. So if x square plus x plus 2, this kind of thing, you see, if you cannot reduce it, you just use the quadratic formula. And if you see square root of minus 7 or minus 5, some square root of negative number, then just introduce the I, and then you get some answer. And of course, you will not have to prove in every math this way, like, okay, this is true, this is true. We are just showing you that this is true for just to build your confidence. Or you also can check once or twice that they are true. So if you multiply this and this, can we get this this 2 thing? So this is what we are trying to prove here. Actually, it does. If we have x minus r, then x minus r, 2 different things, of course. And if we multiply them, this and this, then can we get the actual function? What does it mean? Let me show you that. What does it mean? It looks a lot of calculation here, so it will look crazy. Let me show you what does it mean. Let's use some simple function. Suppose x square minus x minus 6. So the factor of this is, x minus 3, x plus 2, x minus 3, x minus 3 plus 2. Okay, so the real 0 of this function, of course, we will get real 0 here. One is 3, another one is minus 2. So once you know your real 0, suppose now, just for sake of argument, suppose you do not know what was the question, what was this question, just you have only the answer 3 and minus 2. Someone told you that 3 and minus 2, they are the real 0 of some function. Find out the function. So what do? You just write, okay, if it is 3, then the factor must be x minus 3. If it is minus 2, then the factor must be x plus 2. All right. So you can get the factor form. So once you get the factor form, you can think, oh, okay, now since I have the factor, now I can multiply them. So x into x, if you multiply, you get x squared. Then x into 2, so you get plus twice x. Then minus 3 into x, you get minus 3x. Then minus 3 into 2, you get minus 6. Then you have x squared minus x minus 6. And what? See, this is minus 6. This is actually the question. See, this is actually the question. So if you have the answer, if you have the zeros, and if you multiply them by in this factor form, of course, if it is positive, then you will have to consider it negative. If it is negative, then you will have to consider it positive. You will have to change the sign. Then we just multiply them, and we get the question. So if you have this imaginary part, can we go back to the question? Can we get this thing from where we came? Answer is yes. This is just a proof here that we actually get to that place. We can actually go to that place. That's true. So similarly, first you write x minus one of the 0. Then we write x minus another 0. Since we will have to change the sign always Always we can change the sign by inserting a minus. You can say, sir, why minus here in the both place? This is to change the sign. This is to change the sign. Then you have this. You just now, what you do, you just multiply this sign and this sign. Then you will get the change in sign here also, here also. Then multiply x into everything, half into everything, this into everything. Do some addition. It is done here. Do some addition. Then you will get actually exactly the same function from where we started. This is another way to prove that this is, your answer is also correct, and actually we can go back. This is a theory, as I said. This class is theory heavy, so it is possible. Actually, we can go back. Okay. This is the formula. How can we use it more precisely? And then imaginary part, how that drops out from here. Imaginary part, the dropping out. Then let's begin with the fundamental theorem of algebra. This is developed by this guy, and you can see from his picture, he looks nice. This guy is very he's called kind of one of the prodigy. Some people have extreme talent in something. This guy used to have extreme talent in mathematics. His name is Carl Friedrich Gauss. He's from Germany, and this guy, this is his birth year, and this is the year when he died, 1855. This is where he died. This is where he came to the world. This Carl Friedrich Gauss. Okay, he developed the fundamental theorem of algebra. Fundamental theorem of algebra. Such a strong word, Fundamental theorem of algebra. Fundamental theorem of algebra, or fundamental theorem of any subject, any topic, it means that this theorem is so important. This is one of the central concept of entire algebra. You'll be like, oh my God, after all these years and after all this lesson, now we are seeing the fundamental theorem. There are fundamental theorem in many other. There are fundamental theorem in many other fields also. Let's say fundamental theorem of, if you go to UG, you will see that fundamental theorem in the calculus also. Fundamental theorem in the calculus will actually connect the integration and differentiation, both of them. They will connect it. That one, so important. That's why that is so important. That is the connection. That is the bridge. Here, fundamental theorem of algebra, it is telling us that how many roots you will get from a polynomial function. In simple word, I can say that. I mean, everything, all these things, everything what is written here means that. How many roots you will get in a complex, in a function, in a polynomial function. Okay. They said it this way: for every polynomial function, fx of degree n is greater than 1 has at least one complex zero. So this proof is not given here in the book, but one of the illustration of this book is this: for every polynomial function fx of degree n is greater or equal to 1 can be factored into n linear factors. So n linear factors means, see, this is one factor, this is another factor, this is another factor, this is another factor. This way, these are called n linear factors. N is greater or equal to 1 means so that the power is 1 or power is 2 or power is 3 or power is 4, like this way it can continue. So this theorem is telling you that if the power is n, you will have n linear factor, n factors, just in simple word. So n factor means what? N number of real zero, n number of zeros, not real. This guy is not telling you that it will be real. It will be zeros. it can be complex, it can be real. So he's saying that n zeros, and all the zeros will be distinct. That is not also condition. The condition is there will be n zeros. Okay. In simple word, let me tell you in simple word what does all this thing means. Suppose if you have a polynomial function of x to the power 5, then some other things, etc., like 3x cube, etc., etc., blah 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 blah, and then some constant number, let's say 6 or etc., etc. Then there will be, this is the power is 5, so there will be 5 zeros. Not all of them are real, not all of them are distinct. That means there can be a repeating also. What does it mean? Let me tell you. Suppose 5 answers you will get. This is what he is telling. So one answer, suppose one answer is 0, suppose real 0. Suppose another answer is 2. Okay. Then another answer can be 2. Same thing twice. Then let's say 2 complex. This is what he is saying. But he is saying that there will be 5 answers. This is what this theory, all these things are meaning. There will be 5 answers. But some of them may be 0, some of them may be same thing repeating, some of them may be complex. Okay, this way. I mean, I'm saying these are complex, but technically all of them are complex. By now you know. So still we will have to tell it in such a way so that everybody can differentiate it. So suppose a plus bi form, some complex number, imaginary number, a minus bi form. Of course, there is another interesting thing that is actually coming up. If you have one complex number, 1, there must be another one of its conjugate, which is coming up in the next page, in the next slide. So let's repeat it once again. What is he telling? He is telling that if the power is 5, there must be 5 answers. 5 answers means like x equals to, when you find out the final sentence from the final line, you find out x equals to what, x equals to what, x equals to what. And there's the root of the equation. So including real, including imaginary, everything, including repeating, you will get 5, since the power is 5. This is the fundamental theory of algebra, fundamental theorem of algebra. This is also said here, if it has a 0 at x equals to r1, the factor is this by the factor theorem. It has a factor x minus r1, you can factor it by dividing. How can we do it? Then we can continue it if the degree is still more. This is how we can solve it. Once you get, like the previous day also we have seen this kind of method. Like once you get 0, then actually you can factor it, then you can divide it to reduce it. Then if the power is more, then again we try to reduce it. This is the reduction process. Find a polynomial whose zeros are this, and this. This is also very useful concept. See this, how it works. So in this case, zeros are given: 2i, minus 2i, 3, and minus 1. They are the zeros. So what is the question? What is the question? Only answer is given here. Question is what? So this is how we can make the question. Simple. If you get it positive, then write it negative. If you see it negative, then write it positive everywhere. This is plus 1, so it will be x. This is minus 1, so it will be x plus 1. This is plus 3, so it will be x minus 3. This is minus 2i, so it will be x plus 2i. This is 2i, so it will be x minus 2i, and some constant number that we do not know. Some constant number. Now, this will automatically always will put it here, some constant number that depends on we can verify it from the graph if graph is given. So then we can multiply all of them to find out our final answer. So this is the function whose zeros is this. See, this is the function whose zeros is this. So I think now you see another interesting thing, that if this is given, how can we get this answer? the reverse process, reverse kind of reverse engineering we will have to do. Reverse way. First you find one of the factor, let's say +1. If you put +1 here, does answer get 0? If answer gets 0, then you do the synthetic division, you do this part, that part, then ultimately you will see that your answer will come up until here. Like this, from this part you will get this, and then you will get, let me show you what you will get. So you will get x minus 3 after the synthetic division. First you will get x plus 1, then you reduce it, then you will see that for plus 3 the remaining thing is 0. Then all of a sudden you will see x square plus 4 will come, which is not reducible, but since we introduced our imaginary part here, then we can actually reduce it to these two factors. So from this actually we can then go back to our factor also. They are kind of, both way it works. We can go back, we can come back, we can do it. And this is the complex conjugate pair theorem. We will all this complex complex numbers, they will always come in pair. This is what it is called, conjugate pair theorem. Always it will come in pair. So if a polynomial of 3, degree 3 has 0, 1 0 is 2, another 0 is 4 minus 2i, then what is the another 0? Now since we know that degree 3 will have 3 zeros, 2 is given, so there must be another one. And another one, in another one you see 4 minus 2i is given, that means another one is not given from here. This is 4 minus 2i, so another answer will be 4 plus 2i, because complex number will always come in pair, always come in pair. That is the reason. So 4 plus 2i, that is the answer. Find the complex zeros of, find the zeros of complex zeros of f of x and factor it. Apply the rational zero theorem. Possible answer. This is the way how to find out rational zero theorem. First of all, we will start from there. Then we'll try to factor it. So 2 is a 0 of multiplicity 2. We can actually find it out by the synthetic division. And how do we know that multiplicity is 2? Because it will come 2 times. Then our factor is x minus 2 whole square, then x square plus 1. This is irreducible. So this irreducible part actually we can now find it out. And then our answer comes this. So now we can factor something completely. Okay, this is the objective of this entire class. The whole lesson objective is this. Up until before we introduce this complex part, imaginary complex combined this part, we used to keep our function at some place and we used to say, okay, this up until here we can do, we cannot continue it anymore. Now after this class we can actually completely factor any polynomial function. This is participation quiz. You all will try to give a try to solve it. Then if there is problem we can discuss. I think that's all for today, and thank you all. Thank you very much. Have a good day, everybody. See you all in the class. Bye bye.